Kia ora koutou katoa, it's Mrs. Goodson here, and this is the second video about polarity and polar bonds and polar molecules. So the video 10A is all been about polar bonds, and then when you have polar bonds in a molecule, you need to be able to decide and work out whether the whole molecule itself is polar and whether the molecule itself has a dipole. A dipole is a separation of charge. And if you've got a separation of charge in the molecule, then there will be some physical properties of the substance that we can understand because the molecule is polar. So the bonding between the molecules will be different. Okay, so if there is unequalness of sharing in a covalent bond, then we get a polar bond and we get a dipole. So we've got, and the simplest type of molecule is a diatomic molecule. It's just two atoms. So then we're just looking for, are the two atoms different atoms like HCl? Then the molecule will be polar. If the atoms in a diatomic molecule are the same, then it will be nonpolar. If it gets a little bit more complicated when we look at polyatomic molecules where there's more than two atoms, so we must have at least one polar bond and there must be an uneven distribution of charge. And what happens is that if the molecule is asymmetrical, then the dipoles on each bond don't cancel each other out, and you end up with one side of the molecule having a dipole. Now, it's really interesting if you come across these polar molecules and they form polar molecular substances, then they have charge. For example, water is a polar molecule, and so water is a polar liquid. And so, if you rub a balloon and create a static charge sitting on the balloon, you can actually bend the stream of water as the slightly positive and slightly negative ends of the water line up. So that's an experiment you can try. And this forms, so the molecules of water will actually line up, and we use these little delta signs, remember, for slightly positive and slightly negative. And the slightly positive end of the water molecule will be attracted to the slightly negative end. And so our weak intermolecular bonds end up being a little bit stronger, and we say they're hydrogen bonds. That's going to affect the melting points and boiling points of these molecules. So the reason that ice, when the water molecules line up in the solid and form ice, it gives a tetrahedral structure, and it's more open and bigger than we would expect of non-polar molecules. So it's the reason that ice floats. And so that when the ice melts, the hydrogen bonds actually break, and so that's the reason that ice is less dense than water. It's also the reason if you saw the video on ionic solids, it's the reason that ions can form attractions with the water molecules, and that's why ionic crystals dissolve. So this is just a picture. So the fact that ice floats at the top of the ocean, the top of a lake, it means that plants and animals can survive underneath the ice, and that the oceans and lakes freeze from the top. And so it allows fish and other marine animals to survive in cold weather, and our world would be very different if it wasn't for the hydrogen bonding between the molecules. And so water's unique behavior is a direct result of the polarity of the water molecule. As the molecules settle into the solid state, hydrogen bonding forces them into a lattice structure that provides more space between them than they had in the liquid state. And water is therefore very adhesive. It sticks well to a variety of different substances. And because of this attraction, water can get drawn into small capillaries at a steady stream. This enables tall trees to draw water up from the roots. The attraction of water molecules for each other also helps keep fluids circulating through animal bodies. So water is a very, very important molecule in biology. And this is just a slide about how salts dissolve, which we talked about in an earlier video as well. And so these are the symbols that we use, slightly positive and slightly negative. And that shows that there is a permanent dipole on that molecule. That molecule we say is therefore polar. If molecules consist of only non-polar bonds, then the molecule will be non-polar, okay? So like oxygen O2, both atoms are the same electronegativity, so the bonds are equally shared. It's not polar. If the molecule has polar bonds, like between boron and fluorine, this has actually got 3 polar bonds, and there will be a dipole there, and a dipole there, and a dipole there. Okay, so 3 dipoles. But the shape is symmetrical. So in 3D space, there is not one side of the molecule that is slightly positive and one side that's slightly negative. Because the shape is symmetrical, the bond dipoles cancel. So overall, BF3 is nonpolar. So a polar molecule has polar bonds and it's got dipoles that do not cancel out. So in water, there are lone pairs of electrons which make the molecule non-symmetrical, and the dipoles don't cancel out. So this side of the molecule is slightly negative and this side of the molecule is slightly positive, and that means there's a permanent dipole and the molecules are polar. So there are polar interactions between the molecule. So is carbon dioxide polar or non-polar? Each carbon-oxygen bond is polar. However, carbon dioxide is symmetrical and the dipoles cancel, so overall it is a non-polar molecule. Compared with sulfur dioxide, which has this lone pair here, so that you get slightly negative ends of the molecule and slightly positive. It's asymmetrical. Look out for those lone pairs. That makes it asymmetrical, and the dipoles do not cancel, so the molecule is polar. It's not me crossing it out. That's just saying, trying to underline the molecule is polar. So if the molecule has a permanent dipole, it's asymmetrical. The dipoles do not cancel. The molecule is polar. So a polar molecule is any molecule with an asymmetric shape or bonds. Bent and trigonal pyramid shaped molecules are asymmetrical. This is because of the lone pairs. Okay, so this is ammonia. It's got 1, 2, 3, 4 areas of electron density, 3 bonding, 1 non-bonding, and so it's asymmetrical. This example here has different, so these 3 polar bonds are going to be the same, but this one is going to be different. So this end of the molecule is going to be slightly negative, and this end of the molecule is going to be slightly positive. So it's got a permanent dipole. It is not symmetrical because it's only got one polar bond that is different to the other polar bonds. What about carbon tetrachloride? So it's got 4 polar bonds, carbon, chlorine, all polar bonds, but it is symmetrical, so it is non-polar. Non-polar. Not very good at writing with a mouse, but okay. So it's got 4 polar bonds, but it's non-polar. Whereas this one here has got, again, it's got 4 polar bonds, but it's not symmetrical in 3D space because this polar bond is much more polar because chlorine is a lot more electronegative than hydrogen. So they're different bonds. So that is going to have a permanent dipole, slightly negative in that end, slightly positive that end. Because it's asymmetrical, it's going to be polar because the dipoles don't cancel. So each bond has a dipole, but overall the molecule is polar. So first we're going to look for the polar bonds. Then you're going to draw the dipoles over the bonds. Then you're going to consider the shape of the molecule. Is it symmetrical? So do the dipoles cancel? Either the molecule is symmetrical, so the bond dipoles cancel out, and therefore the molecule is nonpolar overall, or the molecule is asymmetrical, so the bond dipoles do not cancel out, and the molecule is therefore polar overall. So you need to learn those phrases for exam questions. You can use this flow chart if that helps you. You're going to look, is the shape a hydrocarbon? It's quite easy to look out for hydrocarbons, and when we do organic chemistry, you get more familiar. They are non-polar. The bond dipoles do cancel. If it does contain polar bonds, then if it doesn't contain, so no polar bonds, then the whole thing is going to be non-polar. If it does contain polar bonds, we're going to go down this way, and then we look at the shape. Is it symmetrical? If it's not, then it's polar, as the bond dipoles do not cancel out. Are all the outside atoms the same? If they are, then the bond dipoles are going to cancel out, so that's something to look for. Whoops. And then this one here, if the atoms are on the outside around the central atom are not the same, then it's not going to be symmetrical, and so therefore the bond dipoles do not cancel out and the molecule is polar. So here's some examples of polar molecules. We've got a diatomic one at the top there. We've got water, and we've got ammonia. They're all polar molecules. Whereas on non-polar, we've got nitrogen here. Oh, sorry, nitrogen's there. And nitrogen's just diatomic between two atoms. And so it's not got any polar bonds. It's non-polar. Carbon dioxide has two polar bonds, but it's symmetrical, so dipoles cancel each other out, so it is non-polar. And this one too it's got 4 polar bonds between carbon and chlorine, but it's symmetrical, so it has got no permanent dipole, molecular dipole. Okay. So an example exam question might compare two different molecules. And so ammonia is polar and borane is nonpolar, and you need to justify the statement. So you say that start with ammonia. It is polar because, remember, looking for the linking words. The nitrogen and hydrogen atoms have different electronegativities. The shape of the molecule, due to the presence of the one non-bonding electron pair, is trigonal pyramidal, which is asymmetrical, so the dipoles do not cancel, and the resulting ammonia molecule is therefore polar. Compared with, in fact, we could have put that in our compared with borane, each BH bond in BH3 is polar because the boron and the hydrogen atoms have different electronegativities. So we've identified that there are polar bonds. In fact, there are polar bonds in both of these. The shape of the molecule is trigonal planar, which is symmetrical. So therefore, the dipoles cancel. And so the resulting molecule is nonpolar. Here's another example. Methane is a nonpolar molecule, and the CHCl3 is a polar molecule, and then you say why. So you need to say about polar bonds and then the symmetry of the molecule. So methane has 4 polar bonds. These bonds are polar because there is electronegativity difference between the carbon and the hydrogen. And you can define electronegativity as the measure of an atom's attraction for a bonding pair of electrons in a covalent bond. So we can just throw that definition in, show that we understand what electronegativity is. The methane molecule is symmetrical in terms of electron density, so the bond dipoles cancel and the molecule is overall nonpolar. Compared that with this molecule here, it's got 1 polar CH bond and 3 polar CCl bonds. The bonds are polar because of the electronegativity difference between the carbon and the hydrogen and between the carbon and the chlorine. Electronegativity is the measure of an atom's attraction for a bonding pair of electrons in a covalent bond. And the molecule is not symmetrical in terms of electron density as the bond dipoles do not cancel, and overall the molecule is polar. So this video 10 has been all about polarity, 10A has been about polar bonds, and 10B has been about polar molecules.